Well, very good evening everybody. Thank you for joining us and the people joining us at home. So coming to today, presentation on a little bit of kit. Quite a lot of you have, but a lot of people have approached me and said, it looks a bit complicated, we're having trouble with it, what can it do? So I put together a presentation for you today, and then hopefully we'll get on with a couple of practical things. And as luck would have it, we have an antenna to test. You can't see that obviously on video, but on the table. So we'll see what frequency we can sort of discern that's built for. So it's titled VNA Revisited. This is based on a presentation that I've done previously about VNA. There hasn't really been much added, as they haven't changed the design of them for not the lower end ones for quite some time. So we'll continue there. So we'll start here. What is the Nano VNA? So the Nano VNA, VNA stands for Vector Network Analyser. Without going into too much in terms of complex sort of history behind that. Your Vector Network Analyser is essentially a device you'll use for analysing various RF components. So it will tell you things such as your inductance, your capacitance, phase angle. You'll have your dB loss or gain if you're using an amplifier. Various other RF characteristics and properties of what you call a DUT or device under test. These things used to be quite big, bulky, in some respects they still are, and incredibly expensive precision pieces of equipment. Now, through the wonder of modern technology, that size has been reduced considerably, as has the cost for us as amateur radio enthusiasts and amateur radio operators. And the way they've done that is actually quite clever. But one thing to understand is that this device is, as Mediocrities once said, good enough. And that is to say that we as amateurs, for the most part, are not looking for precision, expensive equipment. We're looking for something to make our lives easier, to forward our enjoyment in the hobby, and, as anybody else wishes, to make doing things a little bit quicker. So the Nano VNA does differ internally substantially from other desktop precision VNA equipment, and that is something fundamentally to be understood. But for us, it's good enough, and they are fantastic devices for what they are and how much they cost, which is very affordable. I think one recently that I saw on an East Asian reseller, shall we say, was around about £15 to £20, including shipping, which is phenomenal for what it can do for the price, even for 10 or so years ago. Absolutely fantastic. So as it says in the slide behind me, of course, a small cost-effective device that can perform many functions of a vector network analyzer. That's what I've just been through. Most importantly, it's handheld and comes in a small form factor. So you don't want to be, when you're testing characteristics of your new half-wave end-fed, or you're wanting to check how your balance are performing, you don't want to be lugging around a 20 kilogram piece of equipment in the field with you. This thing's absolutely fantastic. So as we progress forward, the working principle of the Vector Network Analyser and the way that they've managed to condense it into such a small package, but quite powerful, is kind of cheating, but it's something that we use on a regular basis, and that's mixing. So what it starts off with is you have a clock generator, in this case it's the SI5351A, and you can send, it looks square wave in the end. That's a limitation of the device, but that comes in useful a little bit later on. Between 50 kilohertz and 900 megahertz is what it will sweep. That is to say, what you can start at and what you can end at, and it will increase in frequency until it gets to 900 megahertz. You'll see an asterisk up there, which is quite relevant, and it's clever the way that it get up to these frequencies, but it does come with limitations and caveats to be aware of. You have three things received, or three waveforms. Received is a bit of a misnomer, it kind of measures it as it goes out. But essentially, you're looking at what goes out and back in through the same port, or an S11 measurement, or an S21 measurement, which is what goes out of one port in the Nano VNA and then into the S21 port. That's typically where you measure loss or gain. For most applications that you'll be using for, specifically SWR measurements, you only need an S11 measurement. You only need to use channel 0 on the VNA itself. The RF is then received by a mixer, and this mixer then mixes it down to audio frequencies, or to the best of its ability to audio frequencies. If you've noticed there, the difference in frequency between 50 kilohertz and 900 megahertz is way outside of the range of the 0 to 20 kilohertz that most sound cards will do. So again, there's a little bit of fudging there in the software, but it's a very clever way of doing it. We can't go too far in depth because that's a talk in and of itself, but we will cover it briefly in just a moment. The sound card itself, in this case the TLV 320, again to be noted, this is in the older versions of the Nano VNA, so the cheaper versions that you can buy now. And some of you do have a different version. There's one with a larger screen, and there's one that has an updated clock and sound card. That varies considerably depending on what you order. As per usual from a lot of these sites, it's a bit of a mix and match. That sound card then converts this analog waveform back into a digital one that the microcontroller will then perform, not quite an SDR, but you can perform calculations on it then internally and display it digitally on a screen, and that way you can get information out of it without the need for a large array of analog filters, which is also how they keep the form factor quite small. So, as complex as it looks, as we have on the screen, is a block diagram of essentially what's going on when you're taking a measurement. DUT, as we've discussed, is device under test. In this instance, what they're measuring is going through a device, so they're using 2 ports. Most likely you're measuring something like a choke or a filter or a trap in this circumstance. Now, when I said it goes up to 200 megahertz, 900 megahertz a little bit later on with the asterisk, this is the key here. As you see, 100 kilohertz to 200 megahertz. It does vary a little bit. Part of the cheat that they're doing is they're using the harmonic. So if you're measuring it, for example, 600 megahertz, they'll be using the third harmonic on 200 megahertz. So when I said it was a square wave, it's worked out kind of intentionally that you can use the third harmonic filter digitally to get the information that you need from that without having to have a clock generator that at the time, they have come down in price now, but at the time could be quite expensive. That can sweep a much wider array of frequencies. As I said before, part of the filtering system on this, well, there isn't one, and that's what comes into the caveat that I'll address at the end of this presentation. You've got your standard crystal clock oscillator at the bottom. That's feeding essentially the STM32, your sound card, and your clock generator. Much of it is kind of a regular thing after this, if you're familiar with microcontrollers. You've got a few inputs and outputs at the left-hand side there. Your LDO is a low dropout, should be a low dropout regulator actually, and a charge circuit for the LiPo battery that you have on the side of it, as you can see there. That's taking care of the battery and power management side. Your push switch and your lever switch to give you user control. You can use a touch screen as well, but they give you the option of some tactile control. SPI LCD. SPI is the protocol in which it communicates with the LCD, much like I2C, or as a lot of you are familiar, USB has a protocol behind it. I2S or I2S there as well. They're all communications protocol, but it's outside of the scope of what we're looking for at the moment. There isn't a great deal to it in terms at least of the block diagram. The circuitry itself is a bit more complicated, I haven't included it. But the block diagram itself is a fairly simple idea. You generate a signal, it's then changed by whatever you're testing, you mix it and receive it via a cheat piece of hardware, and then that hardware communicates with your microcontroller, and then the software does all the heavy lifting on the other side. And it's how they brought the cost down and the size by not having a great deal involved, and all of this is off the shelf, or they're all off the shelf components. You can buy them from various online retailers. Build one yourself if you want. Some of them are quite, they're open source. So, what's actually on the display, it does look complicated. When you first purchase them or get them and turn them on, you get everything at once. They blast you with an array of information. It looks incredibly impressive on the advertising, but it doesn't really tell you much about what's going on. It's all well and good of having all the things up on the display, but if you don't know what any of them represent, then it's a pretty useless measurement tool. So there's numbers around here. The reference to where I got this from, the website at the bottom, is actually wrong. To the numbers the wrong way around, so it's been corrected in this slideshow. It will be different if you follow the link to the website. Just be aware of that if you are following it. So essentially, you have what's called the sweep, and it's kind of self-explanatory in that it sweeps a particular range of frequencies. Something to be noted in the sweep is you'll find that on the edges they look quite jagged, if you will, like there's not a lot of resolution there. Well, that's partly because of the display is quite low resolution. And secondly to that, you only get a certain amount of points. And with any data, you are limited by how much can be processed at any one time. So from 50 kilohertz to 900 megahertz, you're only getting a maximum of a few hundred data points to work with. So you're not going to get a great deal of resolution. So what you can do is you can narrow your sweep so you can have many more data points within a smaller frequency range and then build upon them. There are some applications you can use to connect it to a PC. Again, a bit out of the scope of what I wanted for this presentation, but they will allow you to take essentially as many data points as you want, but in doing so that each sweep of your antenna can take 5 or 10 minutes if you are slicing at 1 hertz per data point, because there's a massive amount of data to get through. So it's a trade-off basically between how much resolution you want within a frequency sweep and how much time you can spend doing that sweep. If you have an antenna that's swaying back and forth in the wind, by the time you get from one end of the sweep to the other, if you've used a lot of data points, the resonance of that antenna has changed and you will get a misleading reading from what you're watching or viewing on the display. Not that I'd advise measuring antennas when they're rocking about the shop, but sometimes that happens, weather permitting being a favourite phrase of many of us. Sweep finish, again, self-explanatory. What frequency does that sweep stop at before it goes back to the beginning and sweeps through the range of frequencies again? Cal status. So I've actually got this the wrong way around, I've noticed this now. Cal status is meant to be number 4, I apologise. So the calibration you'll see on there, C0, D, R, S, T and X. Essentially, those letters will appear on the left-hand side when you follow various calibration procedures. So there's 5 in total, but essentially what you're looking at there is you can choose to do any number of them depending on what you're doing. That's been through a full calibration procedure. So both ports are calibrated, open, load, short, through, and isolation, they call it. We'll go through those a little bit later on. 4 is a marker, 3 on this picture. The markers are essentially just a point that you've chosen, and then you can see the information from that marker up on number 7, where it says your trace. So in this case, where number 3 is pointing, channel 1 in purple is telling you what the phase is at marker number 4. It's usually easier to get rid of essentially everything on that screen. You have your trace is essentially the line that's going across the screen, and your battery, which is represented number 8, that little full charge battery symbol that we're all quite familiar with. That's something to keep an eye on. So that's the fun bit. That's all of the menu options that you can use on the Nano VNA, but there's not much really to worry about when you first start up. We're looking at the top here, probably quite difficult to see, but you'll see it leads on to the little coloured boxes on the right hand side. And to the right of those you'll see off. And that's the important bit. So typically I only use trace 0, so in this case it's yellow. And that basically means you only have one thing on the display to concentrate on, otherwise it can be quite cluttered within the visual field. In this case, when you press the screen, the touch screen, press the screen, on the right hand side you'll have a little menu bar that pops out. You press display, then you press trace, then you press whatever trace you want to get rid of, and then you press off. And that's it. And then you're back on. For now, that's all we'll discuss on this, on the menu screen. Because there is quite a lot to go through, especially when you're calibrating. But that's something we'll cover when we come to actually work on the one from the club on the table, and if you want to bring yours on as well in the practical after this talk, we'll work on them then. But there's a lot of options here, and it can be quite overwhelming when you see it in this manner. But it's all quite user-friendly and straightforward. If you can work out the menu options on your Yaesu or your Icon, you should be absolutely fine with a Nano VNA. So we'll get on to something that you might not be as familiar with, which is the Smith chart. Again, this can be a talk in of itself. It can go on for quite a few days. There's a lot to be gained and ascertained from a Smith chart. But I'll do a very simple explanation because we're not really looking any more in depth in this. As I've said before, we're looking at good enough. So you want to be able to sort of quickly identify what's going on with your antenna system. Again, I've sort of based this around just taking basic antenna measurements, so we'll not go into anything regarding, phase angles or anything like that. So essentially what we've got here is we've got 4 quadrants. Now, the centre is when you hit 50 ohms, so absolutely dead centre is 50 ohms impedance matched. Obviously we're using 50 ohms because we use 50 ohm line, we use a lot of 50 ohms for radio work. Essentially whatever you calibrate your impedance at, you can have 75 ohms, it will be in the centre of that chart. In the top right quadrant, you're inductive and greater than 50 ohms. Top left, inductive less than 50 ohms, and the same goes for the bottom right, capacitive above 50 ohms, capacitive less than 50 ohms. So a quick look at your Smith chart will tell you whether your antenna is more inductive or capacitive and how far away from your impedance you're looking at. Typically, again, with the SWR measurements, you can tell by where the SWR curve is and the frequency, something again we'll come to when we're testing the antenna on the table, to sort of have a quick glance at it and say, right, the antenna's too long or the antenna's too short. So, to clear matters up a little bit in the traces, to just go over it briefly again. So, the main thing is getting rid of all the visual clutter. To remove the trace, you tap the screen, again the menu comes up, you'll tap display, you'll tap trace. You can also double tap on the traces actually, you don't necessarily need to select off. And that usually removes the unwanted trace. What I'm sure some of you will do is what I did the first time, which is you can get rid of all the traces on the display and not realise it, and then it looks like you've broken something. The same applies. If you tap again, it'll bring up an option to bring that trace back again. It's quite easy done, but the user menu is quite user-friendly once you get used to how they've set it up, really. So things to realise when you're calibrating. So when you get given a number of calibration standards with the Nano VNA, they are SMA, and they will calibrate on the SMA port on the Nano VNA. By technicality, if you have calibrated at that point, the only thing that you have calibrated is the SMA connector on your Nano VNA. Ideally, what you want to do is use the connectors that you're going to be using and have a number of some standards. So have some standards. If you're using primarily BNC, you will want BNC calibration standards. Again, because we're looking for good enough, online retailers, you will find them fairly cheap, fairly plentiful. If you use N-type connectors, typically get some N-type standards. If you're using PL259, get some PL259 standards. What you want to do, if you're testing an antenna at the bottom of your garden, you want to calibrate the entire section of line that you are using and all of the connectors up until you plug it in that antenna, and that's where you put your calibration standard. If you don't do that, you will be basically, you won't be looking at just your antenna as its own individual system, you'll be looking at the entire system overall. And you'll end up with some very odd effects because you're counting the feed line as a bit of a problem there. So calibrate where the device that you're wanting to test is going to plug in, using the connector and the appropriate standards that you can get. If you do not have these standards in, for example, BNC, you only have the SMA ones. If you are tempted to use an SMA to BNC adapter, please be aware that that SMA to BNC adapter will change the readings that you receive. In my experience, not by a great deal. Again, we're looking for good enough. Most of the time, that's good enough. As stated there, anything in your signal path should be included when you want to calibrate. You want to get rid of, if you're just looking at your antenna, you want to get rid of as much as you can, providing you are sure that the line you are using is okay. And we'll go through a little bit later on, again in the practical, how you can test that your coax isn't causing you any problems, or connectors. One thing to note actually with the Nano VNA connectors is that SMA, they are quite fragile and will quite happily delaminate from the PCB if you drop it, which, speaking from experience, is not a difficult thing to do, it's quite slippy. So the calibration procedure, I'll go through briefly here for the purpose of the talk, but again we'll be doing it as a practical on the table. You want to reset all the calibrations. It does come sort of calibrated, but again, it's not guaranteed that it hasn't, they've not just uploaded calibration files from the stock that they have when they flash the program to the chip. Those calibrations aren't really appropriate for what you're wanting to use. You'll want to reset the calibrations and start from scratch. If you don't know what you're going to be using it for, if you're just going to be using it for SWR, use the SMA calibration standards and just calibrate the Nano VNA itself. It will be good enough for the majority of use cases. You have different standards. You've got open, short and load, and as they suggest, your open standard is just the cap of an SMA. It's open circuit. You've got your short, suggested it's a short circuit, and load. Load is important. If you are using 50 ohm line, you want a 50 ohm load. If you're using 75 ohm line, you want a 75 ohm load. Looking at the Smith chart, which you can kind of see in the background, what you're doing is you're wanting beginning, middle and end. And then it will calibrate, it can then recognize better where you are within that sort of spectrum. You'll be connecting them to various, well, your two channels. You've got 0 and 1. You do not have to calibrate channel 1 if you're just using this for SWR. Channel 1 can be left to its own devices. And as discussed a little bit previously, the letters that you see on the left-hand side of the screen, you'll only get, I think, 3 of them come up if you've just calibrated channel 0. Channel 1 is used if you're testing things like balance, chokes, filters, traps. It's not necessary for basic SWR readings and can sometimes muddy the waters if you're a bit new to the calibration. It's a little bit different the way that the kind of the terminology with it. You've got isolation through, which can be a little bit misleading. Isolation isn't, you're not connecting anything at all. You're essentially copying what you do from channel 0 to channel 1. But again, we'll go through it as a practical on the table. So there are a number of things post-calibration that you can use this for, as we've been discussing. I'm sure you've all found out. The two most commonly used are standing wave ratio, that's 98% of all use cases. A little bit of hyperbole, but that's mostly what you're going to be using it for, is SWR. And return loss. And that return loss is what you're wanting if you're checking your sort of band stop filters. or high pass filters, low stop pass filters. You're essentially wanting to do a frequency sweep, and you want to see on that graph where it sort of spikes the return loss, or drops depending on how you're taking that measurement. It's a little bit again outside of the scope. But as discussed, it is quite powerful with what you can use it for. So to run through just a quick one with the measuring your SWR, obviously first you've got to select your frequency rate. If you have an antenna with a high Q, as previously discussed, because you have a limitation in how many data points you have, if you do a massive frequency sweep and have a look for where your SWR drops as it goes across in the graph, it will drop. It's quite easy to miss it because there won't be a data point essentially between that. So if you have 50 kilohertz as your Q and your data points are 100 kilohertz apart, it's quite easy to skip right over where you want that. So your frequency sweep wants to be wide enough so you can see whether or not your antenna is too long or too short, but not too wide as to miss the data point entirely. You can use the screen and you can use the jog wheel. What you're wanting really to set your frequency sweep is a stimulus. Again, it comes up on the menu on the right hand side. Stimulus, and it'll be, once you click that, it'll be start and then it'll be stop as a menu option. You can use your jog wheel, but the most important thing here is to remember your channel 0 or your S11 measurement is the port that you're wanting to use for SWR. You're wanting to receive a signal basically bouncing back from the difference in impedance from your antenna. Again, with what we're discussing with the calibration, because you only really need, if you're doing SWR, to calibrate one port, this is why you're only ever using one port. There are limitations and something to be aware of, but you don't often get caught out by them. As discussed with the clock generator, it has a limit of 200 megahertz, so you're using different harmonics. If you come across a point, again, because it doesn't have a great deal of filtering on it, a lot of it's digital, if you come across a point where your antenna is resonant on the fundamental but not resonant on the harmonic that you are wanting to use, it will give you a false reading because some of the fundamental is still coming through. It will still receive the fundamental and sometimes will show you a lower SWR than actually exists on that antenna. VHF and UHF parasitics. This can be a problem if you're holding the Nano VNA. I found with some of them that you, depending on how you're holding it, you'll capacitively start coupling things. The top and the bottom of the VNAs is made from FR4 PCB substrate, and with the centre of it is sandwiched a printed circuit board. If you are holding it and your finger's on the printed circuit board in the middle, you'll start changing a lot of the line impedances internally, and that will also completely ruin your measurement depending on where you're holding it. So if you ever get a chance to get a case for it, keep yourself isolated from it. Battery voltage is another one. If your battery voltage is getting low, although it is a low dropout regulator, you do get to a point where the measurements will start becoming erratic. I'm not entirely sure as to what the cause is, but I found in my own experience that it can really throw off with what you're trying to measure. One solution I did try, and has been used by one of our members, is to use a portable USB-C power bank, which works for your battery, but it also adds a nice little ground tail on the VNA, which if you're measuring at UHF frequencies, becomes significant and can really, again, throw off your measurements. Something else is a lot of the USB battery banks operate on 3.7 to 4.2 volts for your lithium ion cells, and use a buck boost converter or a switch mode converter to bring that voltage up. This can leak through and appear as a signal coming back on one of your channels, and again throw your readings off. It will also, you'll also pick it up if you lay the Nano VNA on your battery charger. You'll see again the measurements move because it'll be a direct pickup from the switch mode harmonics that you're getting on that battery charger. So that's something to be aware of. I think one of the most important things I covered, which is don't drop it because it's quite fragile. And the other one being, a lot of them are open frame, completely open frame. They have no ingress protection whatsoever. they, well, as a result of not having ingress protection, if you're not having a case with it, they are very, very susceptible, as it suggests, to ingress in new and interesting places. And it will gather, especially if the cans aren't soldered down on the board for the RF components. You'll get grime and dirt and dust actually get in there and again change track inductance and line capacitance and things like that. And it will slowly start behaving strangely and you won't know why. And it'll become incredibly frustrating and you'll end up buying a new one and it'll fix it. So these are all things to watch out for, but as the price suggests and the technology behind it, there is limitations. But again, it is good enough for what we want to use. Have we any questions?
A couple of things is, if you are fastening to a long antenna, but remember that the antenna is also receiving at the same time. So
Thank
the
you.
trace
Yes.
will look like, well, you won't believe what it looks like. It looks like a heart monitor in a hospital.
It does, yeah. Yeah, as Max has pointed out there, what you'll see sometimes if you're measuring, I'll give an example as you're measuring SWR, you'll see the trace come across and it'll dip for your SWR. And you'll think, oh, it's resonant. And you'll end up with a big bloody spike in the middle of it, and it'll dip again. And that giant spike is somebody on that frequency, and it receives it, and assumes because it's got a lot of signal back all of a sudden, it's a high SWR. So yes, it can be interfered with signals either side. I found this particularly pertinent when you're measuring 70 centimetre antennas, because anybody using PMR 446, if they are close by, will overload it. And it looks very, very odd. Depending on the size of your sweep, POXAG will do it at 137 megahertz as well, if you're looking at 2 meters, so that is something to be aware of. Thank you. Any other questions?
The other thing I noticed as well is if you plug it into a computer to try and use your VNA with the software provided, the amazing amount of crap that comes down from the USB on the computer, on the power as well. That I had me scratching my head for half a day with what the hell that was.
Oh, it's terrible.
Yeah, absolute garbage.
One thing to note actually about the computer is if you're out and about testing the antenna and you're wanting to do it from your feed line, if you plug it in and hook it up to the PC with, I use Nano VNA saver, you can hook it up and then use remote desktop to view your PC screen. So you can use your phone, if you're at the bottom end of the garden, to tune your antenna whilst you're looking at the VNA itself, back in a shack through your feed line, or it should be, for your whole RF thing. So there's a lot of versatility in that. There's an app now on iPhone and Android, I forget its name. I had it this morning. That you can use to use your phone as well as with the VNA. But if you've already got the VNA, I don't see the point of using your phone next to it. There we are.
Do these work with a long wire, and an unknown?
Yeah.
So you obviously measure at the connector at the other end of the unknown. You're not measuring the long wire on its own. That's okay.
No, you'd measure it. You'd measure it as a whole.
Yeah.
So if you're happy with what if you're happy with what your feed line's doing, you'd measure it the un.
Right. Yeah. Okay.
If you want to know your system overall,
Yeah.
so it's quite useful if your antenna's being a bit strange and it tests fine at one end. Hook it up to the entire feed line. Sometimes you'll find that you've got issues with plugs and things like that. If you just hook it in, it will show us basically a very high impedance antenna, which it is. Yeah. Any other questions?
I'm having trouble with a trap vertical antenna, and it isn't behaving to the handbook, if you like. But making a measurement at the base of the antenna, which would be from 3.5 to 30 megahertz. Am I likely, you're talking about the data, am I likely to see each resonance?
If you
Between 3.5 and 30? Or is that too big a sweeping one go?
in my experience, you'll see resonance. If it's not a very high Q, extreme, then you should see resonance there. It'll pick one of them. For each band, yeah. It might not be very clear, so sometimes all you'll get is what looks like just a vertical line of pixels.
Yeah. But
and
if
more.
you then select a shorter sweep for say 28 to 14,
Yeah.
you're going to get some interaction from 40 and 80 meters.
Yes, kind of. So it is quite sensitive at times if you have multi-band antennas with the clock frequency that's being generated for the RF as a square wave. You will sometimes find that other harmonics will interfere. So if you're measuring at 80 meters, for example, if you have the antenna has another harmonically related band, sometimes it will pick up a reading, if you will, from like
they're all
5th,
harmonically
7th.
related, you see, 28.
Yeah, with it, well, as a multi-band antenna. But yeah, if your antenna is, rather than the white bands, for example, as you said,
So if
yours,
you just go for one band at a time, it's still going to show.
yes, not massively, is
It's
what
gonna
I
show
found
some
in my
interaction,
experience.
yeah.
It will show some interaction, but not
Enough
a
to
huge
throw it
amount.
off, or you think?
Again, good enough. Yeah, if you're not doing a full RF analysis on it, then you might change by 0.2 on your SWR, 0.3.
I'm waiting for better weather.
A wise decision.
I tried a Diamond W8010, which has 4 traps on it, 4 band, and that worked. Tried to run it from, I think it was 5 megahertz, about 35 megahertz, so I could see. And it was a bit blurred at the bottom end with the higher frequencies, but you could see roughly where the point of resonance was. In fact, I had a duff trap on 10 meters. Picked it up.
Right.
Like you say, they seem to be available from all over the place at different prices. And is there something to look out for in terms of, is it not always necessarily the more you spend the better it is, but is it
Yes.
is there certain models or certain things to look for or things to avoid?
As with a lot of gear, if you can buy it from a brick and mortar shop in country, then usually better off because you'll get a better quality with it, although you pay a little bit more. It's a bit of a gamble, depending. A lot of what's on a particular site is drop shipped from the cheaper online retailers. Look at reviews, if they are trustworthy reviews. If it looks too good to be true, avoid it. They all pretty much use the same picture now. There is a list on the Nano VNA open source site. They do like a little list of trusted suppliers. It's not Edfon. Oh, I've forgotten his name now. Teddy something. You can get lists essentially from forums of various things, but in reality, most of the time, one you pick up cheap's just as good as the other.
Murfield Electronics is pretty
yeah.
good.
That's where I got mine.
Yeah, he's a good guy, he's trusted. Or JNC Cheligans, I think is another good manufacturer, that's mine. It's a good one. That's a proper commercial job, all in plastic box, you pay for that.
Is version 4 the latest version?
Truth be told, I couldn't actually tell you because there's a few sideways versions, if you will, as well. There was I think the F had the larger screen, but they changed. I think they changed the clock generator in that. The one that I typically concentrate on is essentially the dirt cheap version. As terrible as it sounds, it's because if you're using them a lot for stroke P antennas or you're out and about, if you break it, it's not a great deal to replace it.
That's the one we got, 2023.
Any other questions? No? Thank you all very much.
We really appreciate you taking the time to watch this video. Don't forget to check the video description where you'll find additional information about the video you've just watched, along with links to products used and to the HADARS website. If you enjoyed this presentation, please feel free to hit that like button. Maybe you'd also consider subscribing and clicking the notification bell so we can let you know the next time we release another video. Thanks again for watching.